Hello learners. Today we'll talk about data organization. Data organization refers to the method of classifying and organizing datasets to make them more useful. This allows and helps you understand why the data was collected, how to use it, and what is the proper way of using it. Data visualization is a term used to describe the use of graphical displays to summarize and show information about a dataset. The data collected for a statistical study are called raw data. It is the set of data in its original form. Basically, an observed data is often described as grouped and ungrouped. Ungrouped data is data given as individual points. Usually it is our raw data after gathering. Example could be the scores of students in a particular class obtained after a quiz. While grouped data is the data given in intervals or bundled together in categories. For instance, a sample of age intervals of women having multiple delivery births in January 2020. Take a look at this example. The final grades of SOC Sci 101 students. This is an example of an ungrouped data. As you can see, we have here 10 rows and 11 columns, which gives us 110 data points. The first data organization that we will discuss is the array. In statistics, a data array is an arrangement of observations according to their magnitude, either in increasing or decreasing order. So, we can arrange the data values from highest to lowest or lowest to highest. But usually, we are sorting data in a low to high manner. One advantage of using data arrays is that observations or measures can easily detect the smallest and the largest values. Also, it is easier to find the measures of position, which will be discussed in the next chapters. Using computers, it is easy to organize data points even with hundreds of observations. With the use of Excel, one can simply sort the data into arrays. First, encode the values in a single column. Next, highlight the column and click icon sort. And finally, sort either from highest to lowest or lowest to highest. In fact, you can use any statistical software. So the final grades of SOC Sci 101 students arranged in an array should look like this. We can see that the lowest value is 50 and the highest is 96. And it is also easier to identify how many times a measure appeared here. Like for a grade of 50, it appeared 6 times. Whereas 80 here appeared only 3 times. Another way to organize data is to use a stem and leaf plot or display. Also known as stem plot, this technique is used to classify either discrete or continuous variables. The stem and leaf plot is an alternative method for describing a set of data. It presents a histogram-like picture of the data while allowing the experimenter to retain the actual observed values of each data point. Hence, the stem and leaf plot is partly tabular and partly graphical in nature. In creating a stem and leaf plot, we divide each observation into 2 parts: the stem and the leaf. For example, we could divide the observation 244 as follows. As you can see, we can split this measure into 2 and 44. The number 2, which happens to be the hundreds digit, goes under the stem. And 44 goes under the leaf. But usually, what we do is we set the very last digit to be the leaf, and what comes before will be set as the stem. So in a case of a 2-digit measure, we could choose the point of division between the units and tens. And 244 can be displayed as such. Take note that the choice of the stem and leaf coding depends on the nature of the dataset. So here are the suggested steps in constructing the stem and leaf plot. To develop the plot, first, we have to list the stem values in order in a vertical column. These are the leading digits of the measures. Next, draw a vertical line to the right of the stem value. This is to separate our stems from the leaves. Next, for each observation, record the leaf portion of that observation in the row corresponding to the appropriate stem. You can list them arbitrarily. But you have to reorder the leaves from lowest to highest within each stem row. Maintain uniform spacing for the leaves so that the stem with the most number of observations has the longest line. Next, if the number of leaves appearing in each row is too large, divide the stem into 2 groups, the first corresponding to leaves beginning with digits 0 through 4, and the second corresponding to leaves beginning with digits 5 through 9. This subdivision can be increased to 5 groups if necessary. Finally, provide a key to your stem and leaf coding so that the reader can recreate the actual measurements from your display. This is like a graph legend to clarify the indicated units of the data value and to avoid ambiguity in reading the plot. In this particular example, the data shows the typing speeds for 20 secretarial applicants. The measures are given in net words per minute. So here is the raw data. As you can see, it is not sorted in an increasing manner. So following the steps of the stem and leaf plot, we first enumerate the stem values in a vertical way. Starting from the lowest stem to the highest stem. Observe that 22 is the lowest and 91 is the highest. And we all have values ranging from 20s to 90s. For the leaf portion, we have to align the leaves with their corresponding stem. In the case of 35, the number 5 and 1's digit should be placed here. But for a stem value of 4, 3 leaves are available. Under the leaf column, we simply put 5, 6 and 7 to establish 45, 46 and 47 respectively. Make sure that there are spaces between leaves. And the same pattern holds for the rest of the stem values. And don't forget this key here. The symbol 2 bar 2 represents 22 words per minute. Another way to organize data is to use frequency distribution. A frequency distribution is a tabular summary of data showing the number of observations in each of several non-overlapping categories or classes. Here, we can have categorical frequency distribution where data are categories such as blood types and year levels. Or we can have numerical frequency distribution commonly known as grouped frequency distribution. In a grouped frequency distribution, the numerical data are divided into classes. This is very useful, especially when the number of observations is very large. Like getting the daily wages of 1,000 people in a particular community. Since there is a big chance that not all workers have the same daily wage, then a range of values is necessary to be easily contain these wage values. Such as 100 to 299, 300 to 499, 500 to 699 and so on. Now, these are some terms to remember in dealing with frequency distribution. First we have the class frequency. This is the number of observations or measures falling into class. Or it shows how many measures are contained in a particular class interval. Class intervals are numbers defining the class. This shows the range of values that a particular class can hold. Also we have class limits. Take for example this discrete interval. These numbers are the class limits. 120 is the lower class limit and 123 is the upper class limit. Here, the numbers 120, 121, 122 and 123 are possible values that this class can hold. Next is the class boundaries. These are true class limits. The lower class boundary or the LCB is usually defined as halfway between the lower class limit of the class and the upper class limit of the preceding class. While the upper class boundary or UCB is usually defined as halfway between the upper class limit of the class and the lower class limit of the next class. So if we have class of 120 to 123, the LCB is 199.5 and the UCB is 123.5. Further we have class size. This is the difference between the upper class boundaries of a particular class and its preceding class. This can also be computed as the difference between the lower class boundaries of the current class and of the next class. But the simplest way to compute this is to look at the difference of the respective class limits instead of the class boundaries. So again we solve the class size of 120 to 123. This is simply 124 minus 120, which is equal to 4. We also have class marks. A class mark is simply the midpoint of a class interval. We just add the class limits and divide the sum by 2. So the class mark of this class interval is equal to 121.5. Lastly, we have this open-end class. This is a class that has no lower limit and upper limit. Usually, inequality symbols are used in these classes. We also include the idea of range. This is the difference between the maximum value and the minimum value of the observations. Let us now examine this example here. These are values taken from the previous illustration of the final grades of SOC Sci 101 students. As you can see, all values are analyzed using a table. We call this a frequency distribution table or FDT. Here, we have 2 possible FDTs. And there are 5 columns here as you can see. The first column shows the classes with a uniform class size for each class. It's clear that the class size is 5. Which can be obtained in several ways. And this is true for all classes. With respect to the first class, we can see that 10 scores fall in the interval 50 to 54. Then it follows by definition that the lower class boundary is 49.5 and the upper class boundary is 54.5. Also, the class mark is 52. If we look at this class here, 70 to 74, the frequency is 17 and the lower class boundary is 69.5. This is the value obtained halfway between 69 and 70. And the upper class boundary for this class is 74.5, which is obtained halfway between 74 and 75. Again, class marker class midpoint is equal to 72. A simple pattern is also observed here in the LCB and UCB columns. Notice that the values here in the LCB are lower class limits subtracted by 0.5. The same pattern is seen here in the UCB, only that upper class limits are added by 0.5. Take note that the number of classes here in this FDT is certainly not the only choice for the number of classes that would summarize the entire dataset. Now, this is another tabular version of the previous dataset. We can see here that there are only 8 number of class with a uniform class size of 6. So the values appearing here in the frequency column will change depending on which class interval they will fall into. And remember, if nothing falls into a particular class, just write 0. And another thing. The sum of all frequencies here should equal to the number of scores in the raw data, which is 110. So how do we construct a frequency distribution table? The first thing to do is to determine the number of classes. As much as possible, try to keep the number of classes between 5 and 15. Depending on the class size, we can have as much as 12 to 15 classes for a much bigger population. For smaller population size, a 5 to 8 number of classes is already feasible. An efficient way to solve for the number of classes is using the Sturge's formula. The variable k here is the number of classes equal to this expression, while big N is the population size. In our previous example, the value of k is this. The next step is to determine the class size. As much as possible, the class size is uniform among classes. A suggested way to solve this is to relate the number of classes k. Suppose C is the class size. Then the class size C is just equal to the range over k. Next is to determine the class limits. The lowest value is said to be the lowest limit. Adding the class size to the lowest limit determines the next lower limit and so on. Generally, the upper limit is obtained by subtracting 1 to the sum of the lower limit and the class size. We stop once the highest value is reached or it is included within class limits. Next is to set up the boundaries. As the pattern shows in the previous table, for each class, we subtract 0.5 to the lower limit and add 0.5 to the upper limit to obtain the lower and upper class boundaries respectively. Next is the part where you determine the frequency for every class. Just count or tally the number of observations falling in a particular class. Again, the total frequency should be equal to the number of observations. We also set up the class marks. The symbol, by the way, is x sub m. Sometimes for simplicity it is just cm. This is equal to the sum of the lower and upper limits, divided by 2. We also have the following variations of frequency distribution. Sometimes, we are interested in the proportion or percentages of observations in each class. So we use the relative frequency distribution. The relative frequency of a class, or RF, is the fraction or proportion of observations belonging to a class. So we have RF equal to the class frequency divided by the number of observations. Another is the relative frequency percentage, or the percent frequency. Denoted by RFP, this is just equal to RF times 100%. A percent frequency distribution summarizes the percent frequency of the data for each class. Then we have the relative frequency distribution, or CFD, which shows the accumulated frequencies of successive classes beginning at either end of the distribution. Basically, we have less than CF and greater than CF. Less than CF is the number of values lesser than UCB of the class, while greater than CF is the number of values greater than LCB of the class. Going back to our given data, we have here the class column, frequency, LCB, UCB, RF, RFP, less than CF, and greater than CF. Again, for the frequency we will have a total of 110 observations. Now, in the RF column, we will use the formula for RF with respect to the first class, and that gives us a value of approximately 0.09. This is obtained by dividing this 10 here by 110. For the second class, we divide 3 by 110 and obtain 0.03 in 2 decimal places. Just continue the process down to the last class. A way to verify that these values are true is to sum up all the values of the RF. And these must equal to 1. Since the RFP is the percent frequency, we just multiply all values under RF by 100 to get a total of 100%. Now, for the less than CF, we'll have to look at the frequency column. Since we are taking values less than the UCB of the class, then here in the first class, we'll have to start at 10. Next is 13. This means that there are 13 observations less than 59.5. Next is 21. So 21 observations are less than 64.5 and so on. Less than CF values can easily be determined by looking at consecutive frequencies. Starting from 10, we just add the frequency of the next class, which is 3, to get 13. So a 13 plus 8 is 21. And so on. The last value here in the less than CF column should be the total observations equal to 110. For the greater than cumulative frequency, 110 observations are greater than the lowest class boundary. So we start at 110. Then the next thing to do is to subtract the frequency of the first class from 110 and get 100 here. Subtract again the frequency of the second class from 100 to get 97. And so on until you get 1 here in the last row. So that is now the complete frequency distribution table. So these are how frequency distributions are displayed. We have the frequency histogram. This is a bar graph that displays the classes on the horizontal axis and the frequencies of the classes on the vertical axis. The vertical lines of the bars are erected at the class boundaries, and the height of the bars correspond to the class frequency. So this is the frequency histogram of our given dataset. Set up first the class boundaries here and the frequencies here in the vertical axis. Next we have the relative frequency histogram. This is a graph that displays the classes on the horizontal axis and the relative frequencies on the vertical axis. Set up first the class boundaries here and then the relative frequencies here in the vertical axis. Remember, the relative frequency histogram has the same shape as the frequency histogram but has a different vertical axis. The main difference between frequency histogram and relative frequency histogram is their input values along the vertical axis. The last representation is the ogive. This is also known as a cumulative frequency polygon. Ogives are graphs that are used to estimate how many numbers lie below or above a particular variable or value in a data. Two methods of ogives are less than ogive and greater than ogive. The less than ogive plots the less than CF against the UCB, while the greater than ogive plots the greater than CF against the LCB. This graph here shows the less than ogive graph of our given dataset. Generally, less than ogives are represented by rising curves, while greater than ogives are falling curves. That's all for data organization. Hope you learned something.